Okay, so most of you are here, so let's start. First of all, how was the exam? Easy, hard, what? Okay, some questions were tough. Yeah, I agree that. Uh, okay, so and these are the kind of questions which maybe you will see in your whatever you plan to do, internship or job interviews as well, where it's not very obvious to see. So it's sort of based on reductions. You are given some unknown problem and you need to connect it with something you already know. Okay. So yeah, so I think the responses also were very varied. Some of you have done well on the difficult questions and messed up the easier. Um, yeah, some of the marks were poor. I think some of you have got negative marks also. But okay, this is just the first real exam for me. Hopefully, you'll do better in the coming ones. Right? So take this as some kind of practice for your job interviews. Okay, so we'll discuss the paper, but not now. So I will share the metal report with you, and so that we'll see. Okay. Okay, somewhere complicated, somewhere easy. Yeah, that's true. And hopefully, it was not too long. You didn't have any. You had enough time to solve them. And I think most of you were doing guesswork. Uh, so maybe if you had thought a little bit about it, uh, you would have found the right answer. Okay. That's the thing about objective papers is that it's very unpredictable and yeah, even a slight lapse can cost. Okay. Let's see if we want to continue with this objective format in the exam or maybe a subjective one, but that at least you get the chance to share your ideas. And of course, so I will share the answer key with you, what I thought was the correct answer. But if you had thought of something else, you had some other idea, you are always free to share that, those things. Okay. And many of those questions were sort of like deductions, right? Because you are given some problem and you are asked which problem we discussed in class to solve it, and that is a theme we will shortly undertake in this course as well. But right now, let's focus on dynamic programming. Okay. So yeah, I will share the marks soon. Yeah, very soon. Yeah, that will be done maybe this week or the next week. I'll definitely share the marks. Yeah, so let's not worry about that. We will discuss the paper in detail, each and every question. Yeah, I will tell you what I thought about. You can tell me what you thought about in the exam, so on. But that's not happening right now because we are waiting for some things, and then we'll share the detailed report with you. Okay. So we are looking at this dynamic programming. Okay, we continue that, and we saw one problem, which is the rod cutting problem. Right? There were two approaches to this, which is the top-down with memoization. So what's dynamic programming is that you guess a part of the solution and then we try all possible guesses. Right? And usually when we guess something, it gives rise to various sub-problems, and an important condition for dynamic programming is that there should be a lot of overlap between those sub-problems. So what are seemingly exponential time problems using dynamic programming, we can get it down to some small polynomial time. So it's a very useful, very general technique. You can apply it to any kind of optimization problems. And there are two main approaches which we saw is that top-down with memoization. So we start with the original problem on input of length n and reduce it to several smaller sized instances, and the solution to these instances are stored in some kind of array. It's a top-down, and bottom-up with tabulation, which is we go from bottom, solve for n equal to 0, then use it to solve n equal to 1, n equal to 2, and so on. And many problems, these two approaches are equivalent, but why we prefer bottom up is that it saves us some space. Okay, so top down sometimes you might need linear amount of space. Bottom up you can just do it with constant amount of space. And we will see the difference between the two. So in the rod cutting problem, basically we were given this rod of different lengths. According to the length, there is a different revenue, and we wanted to maximize, cut the rod in such a way that we maximize our revenue. We did see how dynamic programming can help us, and this was one of the algorithms we saw. Just assume that the first part has length I, and then we cut the rod n times. Okay. Got a n square time solution. So how to do it using top down and bottom up also. Solve sub problems from 0 to n and store in some array. Okay. The only thing we need to make sure is how do we choose this sub problems, and usually it's motivated by this fact is that so we are starting with some guess and we want to try all possible guesses, and then what we want to make sure is what do we guess in the original solution. Okay? That is an important guess to me, and depending on that we get these various sub problems, and the condition is that the dependence between the sub problems should form a directed acyclic graph, right? We don't want any cycles in this graph, otherwise we will get stuck in an infinite loop. Okay? Because one problem is waiting for the solution of other problem, and the other problem is waiting for the solution of the same problem. So that is one thing. One problem with this approach is that if you don't choose these sub problems carefully, there is the possibility of getting stuck in some infinite loop. And in the lab assignments, we will have some exercises which will uh, on this, which will be on this paradigm of dynamic programming. And don't choose as a problem, then you will get some kind of infinite loop. Okay? So that is an important skill to have. And it's and this paradigm not just gives you the optimization version, like what is the minimum value of solving something, but it can also give you an actual solution. What is the arrangement that will give you the minimum or maximum value? Okay. So that is also, we saw something in the last class, and it's just some minor thing is that we just add one extra statement here that successor of j equal to I and return this value s. You'll get where are the actual values where you need to cut that apart. Okay. So today we'll see another example of dynamic programming, which is Fibonacci numbers. Okay. Sure, all of you must have seen this at some point, and they're given this sequence, and first number is 1, second number is 1, and then you just add the preceding 2 to get the next part. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and so on. Okay. And there is a generating function or a standard way to solve this, but we are not interested in that. We just want some algorithmic solution for this problem. Okay. So here is one recursive program, and before pen, which is if n equal to 1, we will return 1, n equal to 2, we return 1. Otherwise, we just add the values of fib n minus 1 plus fib n minus 1. Okay. So just apply this formula and we translate it into some algorithm. And obviously, this is a bad algorithm. It's a sort of recursive algorithm, which is Tn. So what's the Tn? It's the time taken to compute the nth Fibonacci number. Okay. And we need to compute fib n minus 1 and fib n minus 2. For that, add their solutions. That will take constant amount of time. And so finally, this is the recurrence we'll get. T of n equal to T of n minus 1, T of n minus 2 plus fib of 1. And all of you know how to solve this recurrence. And actually, the one thing I noticed in exam that some of you have made mistakes in analyzing the asymptotic complexity, which is higher, which is lower. Okay. I guess all of you are comfortable with solving these kind of equations, but it's equally important to know which kind of solutions are exponential, which are polynomials. That is actually the easiest part of this course. That how you analyze and how do you form this recurrence and solve this recurrence. Okay. So this is the kind of recurrence we have, and it's monotonically increasing, right? So Tn minus 1 is always greater than equal to Tn minus 2. Similarly, the other way, which is Tn is at most Tn minus 1, Tn minus 1 is big of 1. And yeah, so this is the final equation which we get 2Tn minus 2 plus some constant is at most Tn, and Tn is at most 2Tn minus 1 plus some constant. Okay. So we are multiplying by 2 every time, and this, whatever the input size is only getting dropped by 1. So obviously running time is exponential. Okay. So here is another way of depicting this algorithm, which is using this kind of tree. right? So what's happening in this tree is that for computing fib 5, let's say we want to compute fib 5, that is at the root of 3, okay? We need to compute fib 4 and fib 3. Okay? For fib 4, we need to compute fib 3 and fib 2. For fib 3, we need to compute fib 2 and fib 4. Once we get down to this step, it's all. We can solve this from our base case, which is 1, 1, 1. Okay? So this is the kind of computation that is happening. And why do we get exponential time? We want to get down to polynomial time solution. Is that lot of overlaps are there between various subproblems. Right? We are computing fib 2, 1, 2, 3 times. Fib 1 is computed 2 times. And as this value grows larger and larger, there will be lots of overlaps between these subproblems. And therefore, our dynamic programming solution was to store the solution of the subproblems in some array. And then we will use the solutions to compute a final solution to this problem. Okay. And obviously, there are again two ways to do it. Top-down approach and bottom-up approach, okay, which is the basic idea behind both of these is that each value we want to compute only once. You don't want these repetitions like fib 2 is being computed thrice, fib 1 is computed twice, and so on. So we just compute it once and then store in some array, and later whenever we need it, we just pick the required value from that array. Okay. Okay, so let's see how this top-down and bottom-up approaches work. So let me open the relevant file here. Yeah. Oh no. Perfect. Let me go back to the previous. Yeah. So there are these two ways, top down and bottom up. So let's look at this bottom up approach first. And obviously it takes we go of n time because what happens is there are n many sub problems. We want to compute fib1, fib2 up to fib n. Okay. And how much time you need per sub problem. It's just constant amount of time because once we compute that value, we just store in the array. The first few cases take constant time. And then it's just picking the required values from that. So both of them take big O of n time, the top down and bottom up approach. The only difference is the space requirement here. Okay. Question. We can store fib values corresponding to index of array, and if not found, then calculate. Yeah, that's exactly what we are doing, and it. So yeah, so that is what we are doing, and it takes linear amount of time to solve this problem. Okay. Now the main question is, let's say I want to find the value of fib n. Do I need everything from fib1 to fib2 to fib n? Okay. That is the main question here. So what do you think? Do I need all these values or just a few will suffice?
No, sir.
Yeah, why?
Uh, and sir, we don't need this value. So if we don't store them in array and we just use array of length 2 and add add two elements in one element, we can do that. And in that case, storage will not be order of n. It will be just order of one.
Order of one. Yeah. So that's exactly the idea behind this bottom-up approach. Is that notice that for computing any value, we just need the two preceding values, right? Once we add them up, we don't need them anymore. Okay. So the only time we are going to use this one value is to compute fib3. Okay. And once that is done, we can throw away this value from our array because it's not needed for any future computation. Similarly, once fib4 is computed, we can throw away fib2, right? And so every time we just need to store these two values, which are the two preceding values, to compute the next Fibonacci. And that's what is the idea behind this bottom-up approach is that, but if you go by a top-down, then you will need all these things. It will take big offense. So it's entirely up to you. Personally, I like this bottom-up approach, not only because it saves space, but it's also more intuitive. You start from the below and go towards the top. Okay. And yeah, of course, it just uses constant amount of space, so it's very nice. But this doesn't happen every time that you are going to save space and be able to do it in constant amount of space for any problem. Because there are some recurrences, as we saw in the rod cutting problem, the value of the nth number depends on all from 1 to n minus 1. In that case, it is not helpful, but in most cases, bottom up will help you save space. Okay. So, yeah, it's a useful approach, but it's anyways entirely up to you how you want to use dynamic programming. If top down makes more sense to you, you can use that. Okay. Okay. So, any questions so far? Okay, if there are none, we will move on to the next problem. Which is the problem of matrix chain multiplication. So we have already seen matrix multiplication in this course. We saw Strassen's algorithm, divide and conquer. This is a different kind of problem, which is we are given some chain of matrices, and we all want to multiply them together. Okay. Let's say we are given two rectangular matrices. Let's say I'm taken to multiply two matrices. One is a M cross N matrix, other is a N cross T matrix. And that we can assume that just do all these computations. There are some additions, multiplications, and it comes out to M and T. Okay, just multiply the whatever number of rows, number of columns, and finally you'll get an M cross T matrix. Okay. But this is not what we are really doing. What we want is that we want to multiply these matrices using as few multiplications and additions as possible. Okay. Here are some well-known facts in linear algebra is that matrix multiplication is not commutative. For instance, AB is very different from BA. I think all of you know this, but it is associative. Okay. You want to multiply A1, A2, A3. You can multiply A1 and A2 first and then multiply the result by A3. Or you can multiply A2 and A3 first and multiply the result by A1. Okay. And of course, when there is a square matrices, like all of them are n cross n, then none of these approaches, all of these approaches are equivalent, right? So you don't save on the number of multiplications depending on which order you choose. But here we are interested in rectangular matrices. One is M cross N, N cross T. This M could be small, T could be large, or whatever. Yeah, and in that case, this ordering makes a lot of difference in the number of multiplications we need. And that's the problem here, that which order should we choose to minimize the number of multiplications. Okay. So that's the thing about this is that parenthesization does not change the result of a matrix multiplication. Okay. And let's say we have a chain of matrices A1, A2, AN. We will consider, so one idea is we consider all possible parenthesizations and we'll verify the different costs associated with each of them. Okay. So let's say we have these four matrices. A1 is of size 10 cross 100, A2 is of size 100 cross 5, 5 cross 50, and 50 cross 1. And what is the minimum number of multiplications? Okay. So any idea? Minimum number of multiplications. Okay, so we have one idea, which is we multiply A1 by A2, then A3 by A4, and take their product. Yeah, someone is saying something. Any question? Okay, else I don't think there's anything. So there was one more idea, which is okay, just some different way of parenthesizing. Okay, so let's see how to solve this. So what happens when you what's the final dimensions of this matrix? You multiply 10 cross 100 with 100 cross 5, it will give you 10 cross 5. Then you'll get a 10 cross 50, finally a 10 cross 1 matrix. Okay. Obviously, whichever way you do that, you'll always get a 10 cross 1 matrix and it will have the same value. What we are interested in, we want to minimize. There are 5 different ways. Some of you have suggested these ways. Okay. Depending on where this opening bracket and closing brackets lie. Okay. So you can multiply A3 with A4, then with A2, then with A1. Or you can multiply A1 and A2 first and then A3 and A4. Yeah. So actually, this is the right way to do it. We multiply A2 with A3, then A1, and then A4. So let's look at the number of multiplications. Let's look at the first case. Okay. We want to multiply A3 with A4. Okay. So what was the dimension of A3 and A4? Okay. So this was a 5 cross 50, this was a 50 cross 1. So the total number of multiplications will be 5 into 50 into 1. That is just 250. Right? And so we got this new matrix of size 5 cross 1 and we have just used 250 multiplications so far. And then there was this, we multiplied with A2, the result. and A2 was a 100 cross 5 matrix, and we multiplied with a 5 cross 1 matrix. So the total cost here is 100 into 5 into 1, 500. Finally, what we get is a 100 cross 1 matrix. Okay. Then we multiply it with A1, the product, and this was a 10 cross 100 matrix. This is a 100 cross 1 matrix, and the total cost is 1000. Okay. And so these are the number of multiplications we need. Finally, we have the answer to this: 250 plus 500 plus 1000. Okay, this will be 1750. Okay. Then, as one person suggested, which is we multiply A1 with A2 first, A3 with A4 then, and then multiply their product. Okay, so again the same thing. You compute the total number of multiplications for A1, A2. That will give a smaller size matrix probably, and involve a lot of multiplications. So just make those computations, and we'll see that here you'll need 5000 multiplications, and the total size is 10 cross 5. Similarly, here you'll need 250 multiplications, and the total size is 5 cross 5. Okay, and then finally you want to multiply their product, and here the multiplications are 50, 10 into 5 into 1. The final matrix is 10 cross 5. Okay. So this is a very multiplication intensive thing. So you need 5300 multiplications here compared to just 1750. And you can look at the remaining cases, remaining parenthesizations, and compute their product and find the minimum among these values. Okay. So yeah, so this is obviously one way. And particularly when you are multiplying these rectangular matrices, the order of multiplications, that makes a big difference. So it's all about choosing a clever parenthesization, and that will help you solve the problem faster. Okay. So yeah, how do we compute the best parenthesizations? So one idea which we had is we consider all possible parenthesizations and just look at the minimum one among those, which requires the minimum number of. Okay. So here is the formal problem. We are given n matrices A1, A2, An. Each AI has dimension Pi minus 1 cross Pi. And we want to fully parenthesize, which minimizes the number of scalar multipliers. Okay. We say that the product is fully parenthesized if it is either a single matrix or a product of two fully parenthesized matrices. And yeah, so what is the different number of parenthesizations we can have? Okay. So that depends on where you put your opening bracket and closing bracket. Okay. So there are, so you need, that is a combinatorial problem, which is look at all possible ways of fully parenthesizing those expressions. And in fact, it turns out that the number is exponential. So this naive algorithm bad. You can take it as homework. Why it is exponential and what exponent is we are looking at. Okay. So we want to use dynamic programming. And yeah, how will you use dynamic programming to solve this problem? Any ideas? Okay, there is a question. Can you please tell what do we mean when we say A prime? I didn't get the question. When we say a chain of matrices. Uh, so it's just a sequence of matrices which are given to you, A1, A2, AN, and you want to multiply all of these two. And you are given their dimensions, what kind of dimensions they have, and you want to parenthesize those, put some opening bracket, closing brackets so that you can use the minimum number of scalar multiplications. Okay. Yeah. So this is what we call a chain. You are given this n matrices, A1, A2, AN. You are given the dimensions of each of these matrices. Yeah, you want to parenthesize this. Where do you put the opening brackets, closing brackets, and so on. So obviously we want to use dynamic programming here and want to guess something about the solution and to try all possible cases. Okay. So what are we going to guess here? So we make a guess on the last multiplication we are doing. Okay. What is the last step you want to do? Let's say we are multiplying these matrices from A1 to AN. So uh, then you have two matrices. I'm just looking at the last multiplication which we are making, which is multiplying A1 to AK for some K and then AK to AN. The idea is that we want to guess this K, which will give us the optimal number. We just try all possible K. So the sub problems which we have are this. For each pair Ij, we multiply from Ai to Aj, Ai plus 1 up to Ai Aj. That minimizes the number of scalar matrices. And the final dimension of this AI chain. So we need to know the dimension to do any further multiplications with this AI. That's Pi minus 1 cross Pj. Okay. So this is the main idea which we have is that for solving this problem AI to J, for any optimal parenthesization, at the last step we are multiplying AI to K and AK plus 1 to J. Okay. Just look at the last. So this is a very standard tool in dynamic programming, is that instead of solving the entire problem, we just look at what is being done at the last step or the first step. Okay, and that will give rise to your subproblems. Yeah. So how do we decide which value of k gives us the best solution? Is that search for all k, and how do we parenthesize the subchains? Okay, because there is some more parenthesization which we have to do. So again, you can guess some L, multiply from AI to L and L to K, and similarly in this steps, we just recursively find this. So it's a very simple algorithmic technique and can apply it to a variety of different kinds of optimization problems. It gives fast solutions as well. Okay. It's not just that it works only for the problems I do in class. You can apply it to any kind of optimization problems. Okay. So this is also known as what the textbook says, Corman, optimal substructure property. That's just a naming, but you can optimal solution of Aij involves splitting it into two subproblems, Ai to k and ak plus 1 to j. The final step. Okay. And then the optimal parenthesizations of aik and ak plus 1j must be optimal solutions to this problem. AI. Okay, so it's I think fairly straightforward. So what we are going to do is that we are going to store in a two-dimensional array. Okay. So what is happening here, Mij is the minimum number of multiplications needed to compute the product from AI plus 1 to AI. And whenever we need this value, we'll just look at the two-dimensional array. Okay. So how do we define this Mij? So what are the values in this two-dimensional array? And there are some obvious things is that Mij will be 0 when I equal to j. Because when I equal to j, you don't have two matrices. You just have one matrix, which is AI or AJ. Okay. And so you need 0 multiplications in that case. Okay. And otherwise, so this is the base case, is that when I equal to j, put 0 multiplications, and otherwise we just take the minimum of Mik, k plus 1j. Okay. So it depends on how you want to multiply, and that depends on this value k. You need to choose some value of k such that the number of multiplications from I to k and k plus 1 to j, and the number of multiplications you need to multiply these two matrices is just pi minus 1 pj. Okay. So if you want to multiply aij, we are splitting into two parts, ai to k and ak plus 1 to j, and then multiplying these two together. Finally, we want to determine M1 to N because we want to multiply all these matrices together, and that will be stored in this array 1 to N. Okay. And then you just recursively do this thing. just recursively find the optimal parenthesization for AI to AK. Again, you'll get some L, AI to AL, and then AL plus 1 to AK. Similarly for this part. Okay. So this is the top-down approach, and obviously there is this bottom-up approach as well. So Mij is Mik plus Mk plus 1j plus Pi minus 1 Pk Pj. This is what we have. And to compute this Mij, the recursion depends on Mi to k and Mk plus Pj for all possible values of k. Okay. So we want to analyze the time complexity of this algorithm. And so how are you going to choose which one to do first? Because we are doing bottom up, we need some order of computing these values in this two-dimensional array. And one possible order is we look at the chain length. Okay? The smaller chain length gets computed first. Okay. So for instance, we'll compute the matrices with chain length 2 first, M12, M23, M34, and so on. Then come chain length 3, okay, which is M13, M24, and so on. And then comes the chain length 4, which is M14, 25, and so on. Okay. And finally, at the n minus 1 step, you'll have just two matrices, M1 n minus 1 and M2 n. Okay. Finally, we get this M1. And when you just want to multiply one matrix, obviously this diagonal entries will be M11 equal to 0, M22 will be equal to 0. So you can think of this as a matrix where you are just storing the number of multiplications for every pair. Okay. So this is the algorithm which we have in mind. So actually we are given these values P, which is the dimension of those matrices. Okay. And you are given this P naught P1 up to Pn minus 1. N will be just P dot length minus 1. This is the new table or two-dimensional array which we are considering, or you can think of it as a matrix. The rows are indexed from 1 to n, columns are indexed from 1 to n. All the diagonal entries of this matrix are set to 0 because there is just one matrix which is getting multiplied. And for L from 2 to N, so we partition those products according to the chain length. Okay. Obviously, there are many options here to partition them, but this is just one of the ways to do it. You can come up with your own way, but you just need to make sure that you are not getting stuck in some infinite loop. And that is where this choice becomes important. Okay. For L from 2 to N, these two loops, and for I from 1 to n minus L plus 1, we store jth value to be this. Okay. And initially we set all of them to infinity. So this is the usual trick in minimization problems, is that initially you set all of them to infinity, and the moment you see some smaller value, you just update it to that smaller value. And finally we just return the index of this m. Okay, so what's the running time here? So as you can see, there are these two loops happening for L from 2 to N, for I from 1 to N minus L plus 1. So I think it is quadratic time algorithm because we are just doing some comparisons, some additions here. And so it's as I told you many times that it's a very useful technique. Some obvious exponential time algorithms can be reduced to quadratic time by just storing the solutions in some array. Okay. And yeah, this is they will use dynamic programming to solve problems. So any questions on this problem of matrix chain? Yeah, we have a question. In the step where Q is computed, yeah, uh, is MIK already computed? Yeah, it is there in the array. So in the bottom of approach, we assume that all the lesser values are already computed, and it's just this recursive thing, right? So initially you have all these values, MII equal to 0, okay? And initially we store them to infinity and just apply these things and find, uh, update the solution accordingly. Okay. So for instance, if for length 2 things, right? When you have a chain of length 2, okay, so you know how to compute this. You just multiply the dimensions. Okay, so you'll know all these values here, and using it, you find it for length 3 chains, length 4 chains, and so on. So that this all these values, once you have computed it, will store in the array. Why this can't be an optimal partition? AI to AK minus 1 and AK to AK plus 1 and AK plus 2 to AJ. Okay. Yeah, it can be. There's no reason why you can't have this. But it may not be always the case. Because what is happening here is that so why we chose this AI to AK and AK to AJ is that you give me any parenthesization, I can always reduce it to a form where we are multiplying from AI to AK and AK to AJ. But what you are saying here is assuming that we are multiplying AK and AK plus 1 for some K always. That is not necessarily true. So there is one more question. We are first applying the bottom-up approach for computing the multiplications and then running the algorithm. Yeah, I mean, you can use top-down, bottom-up, whatever. Actually, this is not entirely accurate because our algorithm itself is bottom-up. So there is no particular distinction as such. Uh, Where was the inaccuracy? No, so I think it's just a matter of saying things, which is that it's not like we are applying the bottom approach first and then we running the algorithm. I think you are correct in what you are saying, but I'm just saying that this algorithm is based on bottom up approach. So the way to say it is you just compute what is clear to us is that this MII will be equal to 0, MI comma I plus 1 will be just a product of their dimensions and so on. From that, we go down. Okay. I'm sorry, not go down, actually go up. Okay. Then what is the actual computation we are doing? Okay, so I guess there are no more questions. Meet on Thursday.